Hi, welcome to Chemistry. This is General Chemistry Podcast 10.4. Unit 10 is all about thermochemistry, the heats and energy changes involved in chemical reactions and physical changes. So today, I am joined by Nick Higgins and Tom. Tom, what's your last name?
Dignan.
All right. You guys say hi.
Hey, I'm
Hey.
Nicholas.
Okay, so we're going to work on heat of formation first and using Hess's law, which we studied in the last podcast. We'll also look at the vocabulary we use to describe the enthalpy in a physical change, like melting and vaporizing. And then finally, we're going to calculate the heat required to bring about a change in state. So those are the things we're going to work on today. You guys ready for this?
Yeah, let's
Sure,
do some,
yeah.
Oh,
let's do some chemistry.
all right then, here we go. First of all, let's define what the heat of formation is. Essentially, it's the change in enthalpy for the formation of 1 mole of a compound from its elements. I mean, that's not too hard, right? Heat of formation describes the enthalpy of forming a compound, right? This is only for a compound, though. So let's look at this symbol right here. The delta means change. So we talked about the change in enthalpy. And then this little zero means that we are in standard conditions. In thermochemistry, standard conditions means a temperature of 20 degrees Celsius. And do you know what pressure?
1 atmosphere.
Hey, that's a good guess. Yep. Pressure is 1 atmosphere. In the gas chemistry, standard temperature was 0 degrees Celsius because those numbers are easy to work with. But those chemicals are not easy to work with. To do a chemical reaction with frozen water is pretty tough. So we changed the standard temperature for all other chemistry except for gases. All right, so here that is again, this delta H symbol, and it's 0 kilojoules per mole if you are dealing with a pure element, like something on the periodic table. You know, it's called the periodic table of elements, right? Anything on there has a heat of formation of 0 kilojoules per mole because we don't form them, we use them in our reactions to form other things. So anytime you see an element, even one like this, oxygen with 2 atoms, that's pure oxygen. That's the way it comes, right? So any of those Brinkelhoff guys, we got to put 0 kilojoules per mole. And we can use this then, the heat of formation, to calculate the heat of any reaction or the heat of formation of something that we don't know. We can use a reaction to figure it out. So that's what we're going to do.
Very nice.
Yep. And here's how. We're going to use Hess's law. And Hess's law says that you simply take the heat of your reaction to be equal to the sum of the heat of formation of your products minus the sum of the heat of formation of your reactants. So just to remind you, this sigma is a Greek symbol that means sum. And really, in fancier printing, it would have like a little doohickey on the ends like that. This is just the font I picked, and it simplifies it a bit. And then the N in front of here represents the number of moles from your balanced equation. So that's what all of those things are in there. And I think if you see us use it, it'll make a lot more sense. So let's use it. Nicholas is an expert at this. He's done this before.
Exactly.
All right then. So here's what we're going to find out. The standard heat of reaction. Standard means it has to have a little circle. Standard heat of reaction for the following reaction, where we have 2 carbon monoxides. Let's not confuse that with carbon dioxide.
No.
And we're going to combine it with oxygen gas, and then we'll make carbon dioxide. Okay?
Sounds good.
All right, then we need to know the heats of formation of all of these guys. And I got that table ready, and you guys got your book ready. What page are we on, Tom?
Page 530.
Okay, so page 530 in your chemistry textbook has a table that looks like this, only I think theirs is in color, right? Theirs is blue.
Yeah, it was a blue title. So.
Okay, yeah, so look for table 17.4, and the substances that we're looking for are carbon dioxide gas, so right here, And we need a carbon monoxide and carbon dioxide. Let's make sure we get those numbers in the right places. So carbon monoxide is a negative, no, well, now I can't read it because I circled it. Negative 110.5. Okay, so I'm going to write that underneath the carbon monoxide, negative 110.5. And since my CO is multiplied by 2, I'm going to multiply that number by 2 as well. All right, and then CO2, let's go back, was negative 393.5. So I'm going to write that underneath my CO2. Oh, no, I went too far. There we go. Everyone just saw all the things that are open.
Done it again.
I know. Negative 393 was at 0.15?
0.5.
0.5. Thank you. And since that one's multiplied by 2, I'm going to multiply the number by 2. All right, so this is my products. Whoops, I don't want that mark there. How about oxygen? That was not on our table.
Because it was an element.
Right, so its heat is
0.
0. Okay, so now can I just add all of these up and I'll have it?
No.
No, that's not the way it works. We take the sum of the products minus the sum of the reactants to get the heat of our reaction. So our products are on the right-hand side, and all that we have is 2 times negative 393.5, and we take away from that the sum of our reactants, 2 times negative 110.5. Well, I was going to make big brackets to hold all of my reactants, but I don't have to, because we don't have to put oxygen in there, huh?
No, there's no need. It's an element.
Right. Okay, so while you work that out on your calculator, I'm going to show everyone how to do it with my calculator. We want to make sure that everyone gets the same answer as me. Because you know what happens when you get the same answer as me?
We're doing something right.
Yeah, exactly.
Yes.
All right.
The teacher's wrong.
Well, when does that ever happen,
Happens
Tom?
sometimes.
Oh, yeah, it does, especially in my class. You just told everyone my secret. Okay.
Thanks, Tom.
Yeah, thanks.
Welcome.
2 times negative 110. You're probably way ahead of me now,
Of course.
as usual. And close my parentheses, because I want to force my calculator to do the order of operations that we want it to, right?
Yeah.
Okay, I got negative 566.
That's what I got.
Well, that's a good sign. If you and I both agree, I think we're on the right track. Negative 566. And what were the units in our table?
Kilojoules per mole.
Okay, then our overall units are kilojoules per mole. Well, that didn't seem so bad. Products minus reactants, and there you go. And then we'll all put a box around the answer, because that's the way I like it. It's a good reason. Okay. My little arrow's back, and let's try another one. Hey, I got a table already. We don't have to flip around for it. Okay, but I'm going to use the same strategy, because I like to put the numbers underneath the substances. That helps me keep them straight. So methane, it looks like, is a negative 74.86. Okay, and then oxygen, you told me before, is a 0, but what if I have 2 oxygens?
2 times 0, which would still be
It's still
0.
0. Okay, well, that seems easy enough. All right, and then CO2 is still negative 393.5. And then water is a negative 241.8. Be careful about which phase of water you're dealing with. If you're looking it up in your book, then you'll see a liquid and a gas phase. So, Tom, can you see which one has the negative 241.8?
It's H2O.
Gas.
Yes.
Okay, so water vapor has this enthalpy, but liquid water would have something different.
Yeah, it's something like negative 285.8.
Right,
Yeah.
okay. So we have to be careful to use the one that they're asking for. This, I just told you what value to use, but if you're looking in your book, make sure you have the right phase. So we're going to find the heat of reaction, the enthalpy change for this, and we're going to use Hess's law. So we'll take products minus reactants. All right. Let's see, I have two products this time. So I'm going to make a parentheses like this. It's called a bracket. So we'll take negative 393.5 and add that to our other product, which was 2 waters. So 2 times negative 241.8. Okay, so that's our products, all of that. And from there, we're going to take away the sum of our reactants, and oxygen is going to only contribute 0.
Yes.
So,
2 times, by the way.
yeah, right, which still adds up to nothing. Because nothing plus nothing is always nothing.
Yes.
All right, and so there's our reactants. And you've got your calculator going already. I better catch up.
It's alright, you're doing fine.
All right. So helps when you turn the calculator on. Negative 393.5. And then I'm going to add 2 times negative 241.8. Okay. So there's my products. And I'll go ahead and write that down. Is that what you got for products?
No. Let me make sure I got this all right.
Okay. Did you use your negative signs? Because I have 2 negatives here to add together.
Wait, Nick, you got negative 802.24.
Yeah.
Hmm.
Yeah, hold on.
Okay, we'll double check. That's all right. Our folks who are following along at home, they're going to need some time to work this through also.
Just checking stuff out.
Okay, and I'm looking over mine too, what's printed on this pane.
Oh, you forgot to subtract. I just did it automatically.
Oh, okay, yeah, I haven't subtracted this end yet.
Yeah.
All right.
That's what's up.
Okay, so we're not different, we're just not in the same place in the problem.
Yeah.
Because now I'm going to subtract the negative 74.86 from here. So subtracting a negative number really means that, right?
Yeah.
Yeah.
Okay. So
That's what I learned.
yeah, so then that's what I'm going to do on my calculator. So I'm just going to push plus 74.86, and now I bet our numbers are going to match. Yeah.
Yep.
They sure do. Okay, so I get minus 802.24, and just because my calculator checks out all these numbers, does that mean I get to keep them?
No.
No. How many sig figs should we keep here?
You should keep 4.
Okay, 4 sig figs, so 1, 2, 3, 4. Looks like we can just check that out. Yeah. Okay, so 802.2 kilojoules per mole, and I'm not going to put my box around such an ugly scribbly number. We're going to write that nice and neat, 802.2 kilojoules per mole for this reaction. That seems like a lot of energy, and it's being released, right, because that's a negative enthalpy change.
Yes.
That means that's exothermic, and that is highly exothermic. Negative 802.2, that's a lot of energy.
That is.
Yeah, guess what reaction that is? CH4 plus 2O2s, that's the combustion of methane.
Okay.
Yeah, that's the stuff we do with the Bunsen burner.
Yep.
Yep.
Should produce a lot of energy.
Right, that's why we do it. That's what we do in the lab. All right, well, that wasn't too bad either. I bet we can all handle that. You ready for a challenge?
Let's do it.
All right, you asked for it. Remember, it's all Nick's fault.
Not mine.
Not Tom's fault. Okay, so let's read this problem carefully. We have a reaction that I don't really know what this is, but I'm going to guess it's phenol, because after the comma, they tell me that formula, C6H5OH.
Yeah,
It's a very good guess.
Yeah.
Hey, thanks, I like to use my noggin. And we have 2 grams of that stuff. A 2-gram sample of pure phenol is completely burned, according to the equation above. And all my students learned about combustion before. Every time you have a reaction between oxygen and a hydrocarbon, it's going to make carbon dioxide and water. And so that's what we have here, carbon dioxide and water. So then the rest of it says, after we completely burn 2 grams, we get 64.98 kilojoules of heat released. Okay, and that's for 2 grams.
2 grams.
So then the question, part A, asks to calculate the molar heat of combustion of phenol. So that means we want our enthalpy of this reaction in molar heat. So that means kilojoules per mole. Well, I know how many kilojoules we got from 2 grams, but I don't know how many kilojoules we got from 1 mole, because we didn't burn 1 mole.
No, we did not.
No. Can you think of a strategy to get from grams to moles?
Find the molar mass and then divide by how many grams you have.
That ought to work. Sure.
Should.
Okay. So all we need to do now is figure out how many moles we have. So we'll take our 2-gram sample of phenol. So I'm going to abbreviate this guy and call it pH. Does that work for you?
Yeah.
All right.
Working with acids and bases.
Yeah, not that same kind of pH.
Yeah.
All right, now we need to know how many grams are in a phenol. So we've got to have 6 carbons, and 1 carbon is 12. 6 times 12 is 72. And then we have, let's see, a total of 6 hydrogens and 1 oxygen. So,
I got 94.12.
can I trust you?
I believe you can.
All right. You're usually pretty trustworthy with those things. All right, so that's how many moles of phenol we have. Nope, that's how many grams are in 1 mole. Now let's take 2 grams divided by 94.12.
And you get a bunch of calculator vomit.
Calculator vomit, I want it all.
Okay, so 0.0212494688.
Okay, and that's how many moles of phenol we have. Now I asked you to give me all of those numbers because we're not done with our calculation yet.
You shouldn't
Right.
estimate yet.
Yeah, so if we round too soon, then we could introduce errors into our calculations.
Big errors.
Right, so we want to keep all the digits in the calculator, and you guys at home don't have to write all of these into your answers every time. It's okay to round something smaller in your writing, but not in your calculator. Keep
Never.
that number in your calculator. So we have 64.98 kilojoules from this many moles. So we're going to take our kilojoules, 64.98. I'm trying to make a 4, and it didn't turn out to be on. There we go. And that's kilojoules total. Now let's divide by the number of moles. 0.021 and all that junk, right? Because it's still in our calculator. And we'll get how many kilojoules there were for every 1 mole. That's what the molar heat of combustion is referring to. So Nick's going to type that in, but I want to show everybody how to do it with the calculator. Okay, so we take 64.98 and divide by, whoops, too many divides. My calculator got hung up. My little pen doesn't like my calculator very well. 0.02124. Did I write down all the numbers right? 94688.
You put a negative instead of 6.
Oh, that's lovely.
Yeah.
And now I put another wrong thing. Okay, so we want this to be a 6, and I can't get my mouse to move. Now I put alpha. Okay, 6. Yay, got it. Okay, is that what you got?
Yes.
Good. 3058, we'll call it. Kilojoules per mole.
That's a huge number.
That is a lot of energy. But again, it's a hydrocarbon and it's combustion, right?
Yes.
So we can expect to get a pretty big number. All right, well then let's come back to the question because part A is done. We better put a box around it so we know that answer is done. And let's look at part B. Now it's asking us to calculate the standard heat of formation of phenol in kilojoules per mole at 25 degrees. So the heat of formation is not the same thing as the heat of reaction, right?
No.
Because the heat of reaction relies on the heat of formations. Now we're working our way backwards.
Yeah.
Okay, we're going to solve something different from Hess's law. So I'm going to use the reaction we have and write out what Hess's law says about this. The heat of reaction, which in this case, our reaction is combustion, right?
Yes.
Is going to be equal to our molar heat of combustion. And that can be described by Hess's law. So it's the sum of all of our products. So I'm going to put the heat of formation, what's our product of? CO2.
And H2O.
And we want 6 of those. 6 CO2s. And H2O, how many H2Os?
3.
Okay. So 3 waters. And it's liquid water. So we'll be careful to use the right number here. Oh, that was the parentheses. And then we'll take away from that the sum of
The
reactants. And so for one of our reactants, we have phenol, and there's only one of those guys, right?
Yes.
And I'm just going to call it pH. And in addition to that reactant, I have the heat of formation for oxygen. And there's 7 oxygens, but it doesn't matter how many oxygens we have. They each only contribute 0, right?
Yes.
And so 7 times 0 is still 0.
It's not worth it.
Right.
No.
So what I see here is that this problem is working out to be not quite as complicated as I initially suspected. Whoops. So
Not bad.
let me just show you here what we're going to do. Here's the plan. We want to get this guy by himself. Okay? We already know the heat of combustion because we calculated that before, and you're going to have to remind me what that number was.
The 3,058.
Yeah. So around 3,058 kilojoules per mole. Now we're not going to round that number in our calculator, so keep that number handy. All those sig figs there. Okay, and then this heat we can read from the table right over. CO2 is right here. Okay, and then let's just put that in. So I have 6 times negative 395.5. I'm going to have to move this guy out of the way. And then we're going to combine that with our other product, which was liquid water. So that's the only choice we have for water, negative 285.85. Okay, so then we add these two together, because that's our sum of our products. And we take away the sum of our reactants, which is the thing we don't know. This is what we're trying to figure out. And then the water, I'm just going to leave it off because it makes 0. Okay?
Very good idea.
All right. So this looks like a pretty basic algebra problem.
Pretty basic.
Once we know what this total is, we're going to take it away from the other side.
Shouldn't that 3,058 be just positive?
That's a good question.
Because we calculated it to be positive.
Oh,
earlier.
okay. But look what this says. That heat is released. What do you know about exothermic reactions?
Always negative.
Always negative.
Right, right, exactly. So I'm glad you asked. That's good to clarify. Good.
Just had to make sure.
Yeah, well, I'm glad you did. Because everyone else was probably wondering why I just randomly put a negative there. But it wasn't random. I did it on purpose. All right, well, you know what? I'm going to get my calculator. Not because I think you're going to do it wrong, but because I think I could do it wrong easily. So I want to make sure everybody else knows how to do it. I'm going to need to move this line or that's going to interfere with what we're doing. Okay, so what do you think? Should I find the sum of this first and then subtract it across? That seems to make sense to me.
Yeah, that's what I believe you should do.
All right, so 6 times a negative 395.5. And then I'm going to combine that with 3 times a negative 285.85. Oh, that hung up here. Come on. 0.85. This pen thing, Tom, is a little complicated. It's kind of annoying. Okay, so there's the sum of my products, negative 3239.55. Okay, so when I move that across to the other side, it's going to have to change its sign.
Yeah.
Right? So I'm just going to take 3, nope, negative, here's my other side, negative 3058. And this time I'm going to add 3293, nope, 39.55. My brain and my mouth don't want to do the same thing to me.
We all have those days.
Oh, good. I'm glad it's not just me. Okay, so I got 181.55 is equal to, on this side, the minus delta H of formation for pH. Did I solve the problem yet?
No.
Oh, but I did all this work. What do you want me to do next?
Find the exact number for the heat of formation of...
So not for the negative heat of formation?
No, the regular.
Okay. Well, then I'm going to have to multiply both sides by -1, which in math language just means change the sign, right? Change the sign, dummy. Okay, I can do that. Don't make it harder than it needs to be, right?
Yeah.
And then our units, of course, are in kilojoules per mole.
And I got 172.59 instead of 181.55.
Oh.
But you used 3058 instead of the...
Right, I used the rounded number, and Nicholas had that number in his calculator that was not rounded. So I think I like your number better.
Okay.
So with 4 sig fix, let's have it.
172.6.
172.6 kilojoules per mole.
So we better use every number.
Everything in your calculator.
Right?
Yeah, because when I did not do that, I got the wrong answer. Yeah.
Pretty useful.
Yes, that's good to know, right? Gotta know how to do this correctly. Okay, well, that's the hardest problem that I'm ever going to ask my students to do. And I'll give you guys a secret if you don't tell them. This is their bonus problem. Yeah.
You know the podcast is recording all
Oh, that's right. We just told them. Well, now everyone knows.
You ruined your surprise.
They better get it right then.
They better get it right. Everyone's going to get a bonus, right? Unless they decide that's too much trouble.
And they're just like, eh.
Yeah. Have you ever known students to act that way?
Yes.
All right, well, let's do something easier, okay? Changes of state means that we're going from solid to liquid to gas. Those changes, that's what we're looking at now, not chemical changes, but physical changes. So this one is kind of a no-brainer. You already know how to melt ice, right? If you want to melt ice, what would you do to it?
Add heat.
Add heat. And adding heat is?
Endothermic.
Endothermic, right. So here's what we call it, the heat of fusion. And its symbol is delta H fuse. And it's endothermic process. Yeah. Well, let's do the opposite of melting, freezing. Going from a liquid to a solid. So we're going to add heat or take heat away?
Take it away.
Yeah.
Right, taking heat away makes that process exothermic. And we call it the heat of solidification. And its fancy symbol is delta H solid. Okay? So far, so good? I know. Isn't it solidification instead of freezing? Because delta H freeze, I don't know. That just wouldn't look right. Nah. Vaporization is when we change a liquid to a gas. So we're going to add heat for that to happen. Endothermic. And we call it delta H vap for heat of vaporization. How about condensation? What do you think?
the opposite of vaporization.
Right, opposite. So it would be exothermic. Obviously, you have to take the heat away from a substance if it's going to condense from a gas to a liquid.
Of course.
Right. Okay, the next one is sublimation. And my students probably remember what this is, going from a solid to a gas without ever being a liquid. Not very many things do that, but carbon dioxide is one, and so you can buy it at the grocery store as dry ice.
Oh, that's fun.
Yeah, it is fun stuff. Makes all that fog. So we call this heat of sublimation, or delta H sub, and for that to happen, sublimation is, I would have said exothermic, wouldn't you? You got to heat
Yeah.
it up? No, endothermic. You got to heat it up
Yeah,
to make
yeah,
it happen.
that's right.
I was confusing my own self. Sorry, guys. Okay, deposition's the opposite. That's the one that's exothermic. If you release the heat from a gas, it can turn back into a solid. Heat of deposition.
Very true.
Yep. And then the final one, heat of solution, means we're going to try and dissolve something. So this is not really a state change. If you have something solid that you dissolve in water, then it becomes aqueous, but it doesn't change from a solid. It's still a solid particle. It's just now ionized and completely surrounded by the water. That's how we get it to dissolve. So whether or not that works very well depends on what it is. So we cannot really predict if it's endothermic or exothermic. We just have to try it out and see. So we'll probably do this in my class. Get a temperature probe out and dissolve something in the water and see what happens. See if the temperature changes.
Sounds like an experiment to me.
That's right. In-class demonstration. And you know what, folks? I can guarantee you, if we do a demonstration, the temperature's going to change because I'm going to pick the right stuff. You know me.
Yeah.
Yeah. All right. Let's do an example. Why does it say example 2? Are we on like 3 or 4 or 5? I don't know.
Well, it would either have to be example 1 or example 5.
Right.
And it's neither. So therefore,
I have made a mistake.
yeah.
Oh well. I think we can handle it.
But can they?
I hope so. They've seen me make mistakes before. So have you.
Let's hope.
Spend enough time in my classroom and you'll see it a lot. Okay, so we have some liquid water. Oh, wait. This is our second example.
We skipped one?
I think we did. That was Tom's first guess. We skipped one.
Yeah, it was right.
Yeah, there it is. Example
Yay.
1.
Glad you're here, Tom.
Doesn't happen
I
often in
know.
chemistry.
Good job, Tom. Okay, so we're going to find the heat of fusion, and we just learned that vocabulary, but that doesn't mean you remember it. Heat of fusion. What process is that? I know.
Endothermic.
Everyone at home has that little chart in front of them. This process, heat of fusion, is melting.
It's endothermic.
Endothermic.
Endothermic, right.
That's right.
Okay, so
Nice.
the heat of fusion for water is 6.01 kilojoules per mole. So that means in order to melt water, we have to add this much heat for every mole of water that we have. So the question is asking, how many grams of ice will melt if we add 2.25 kilojoules of heat? Well, I don't know, but I can get how many moles would melt,
Yep.
right? And from moles, I bet we can get to grams. Because it's just water, right? Ice is water. We can calculate the molar mass of water quite easily. So how many grams is our target? And our starting place is 2.25 kilojoules. And we're just going to rock out a T-table here. So I'm going to put my starting place on the starting line of the T-table. And then how should I put this in there? Kilojoules on the top or on the bottom?
Kilojoules should be on the bottom so they cancel out.
Okay, so then this number has to go with it, 6.01 kilojoules for every 1 mole.
And 1 mole would be at the top.
Right. Okay, now let's change moles to grams. 1 mole of water, my students probably have this memorized, is 16 plus 2 hydrogens, so 18.02 grams.
If they don't, they should learn that.
Yeah, I think so. It would come in handy, right?
Very.
Yep. Okay, let me get my calculator out. Yours is already out and done, probably, huh?
Yeah, I'm done with the problem.
That's typical, by the way, of Nicholas Higgins in my class. He's done with the problem before I even turn on my calculator. 2.25 kilojoules.
Sit to 200 calculator.
And I'm frozen. Let me go. Okay, 2 over. What do you want from me?
Nope, that's not right.
2.25.
Some
Then we're going to
little
divide
technical
by
problems.
6.01. And I'm going to hit enter because I want to do that part first. And now let's multiply by the next step, 18.02. You notice anything that's on the bottom, I divide. And anything that's on the top is multiplied.
It's like individual fractions.
Yeah, exactly. And then here's my result, 6.7, let's see, 3 sig figs, right? So 7.5 grams of water. Now, did you and I come up with the same number?
Exactly.
Hey, I like it when that happens. Put a box around it, because that's the way I like it. It's a good reason.
Yeah.
Okay, well, I think we get the point. A T-table is easy. So let's figure out what is this one asking for so we can set up the next T-table. How much heat? Oh, there's our question right there. How much heat in kilojoules is absorbed when 24.8 grams of liquid water at 100 degrees Celsius and 101.3 kilopascals is converted to steam at 100 degrees Celsius? Is that the temperature at which liquid water turns into steam?
Yes.
Right. So is it okay for us to have both liquid water and steam at the same temperature?
Yes.
Sure.
Yes.
Sure it is. Especially at standard pressure, right? That's the temperature at this pressure for which water turns into steam.
And it can also be a liquid.
Right, it could be both at that particular temperature and pressure. Right, so we have both liquid and steam at that same temperature. You see, if we added more heat, we would just turn all the liquid water to steam. We wouldn't be changing the temperature until all the liquid water's gone. Then the temperature would start to increase, and we'd have to use this dandy equation, MC delta T, because then our temperature would start to change again.
Yes.
Yeah. We've used that before, but we don't need this for this reaction. We just need a T-table. So we know the standard enthalpy of vaporization, that's going to be our conversion factor. We're going to start with 24.8 grams. And we're trying to get to kilojoules overall. Okay, so 24.8 grams of water. And we better change this to moles because my conversion factor has moles in it.
Yes.
No problem. It's water. So 18.02 grams per 1 mole. So just like we already know how to do, put the grams across so it will cancel out. And then now comes our conversion factor. I better put moles on the bottom this time, right? 1 mole goes down here, and then the number that goes with kilojoules
So
is
they can cancel out.
40.7. Right, we want moles to cancel out. And then when moles cancels out, we're left with kilojoules, and that was our target all along. So once you get to where you're going, you better stop. Okay, calculator time. Oh, we got too much stuff on there. And this is in my way. Can I get it? Yep, I can. Good. So 24.8, my next step is on the bottom, so I'm going to divide by 18.02. And I'm getting, okay. So I'm going to hit enter there.
Install now. Install now.
And then multiply by 40.7. Believe it or not, if I clicked install now, it would ask me for my administrator password because IT doesn't let us install our own updates.
That's not right.
I know. So, okay, 3 sig figs, 56.0 kilojoules of energy to turn 24.8 grams of water. That's about 25 milliliters. I think
A
it's
little
about a
less,
half a
yeah.
cup, right?
Mm,
Something like that.
sounds about right.
Yeah, I don't know. I'd have to check my measuring cups at home because they actually have milliliters on them.
I don't know the conversion from cups to liters.
Yeah,
I've
we don't.
measured out 25 milliliters so many times.
Yeah, you know what though? I know that 330 milliliters is the size of a 12-ounce soda can.
Yeah.
Yep. Because when you're in Europe, they measure
Yeah.
things in 33 centiliters, right?
Yep.
Yep. They put a little mark on your glass for that.
Uh-oh. Another question.
Yeah, we have another question to deal with. So I better. Uh-oh, what did I do? What did I do?
Cleared the wrong thing.
I did. We'll clear that thing. So here's our next question. How much heat must be released to condense the same amount of water vapor to liquid water under the same conditions? So how much did we use? 56 kilojoules?
Yeah.
Okay. It took us 56 kilojoules to turn the liquid water into steam.
Yes.
So now we want to go backwards and turn the steam back into liquid water. How much energy is that going to take?
The same amount.
The exact same amount.
Right, the
If it's
exact
the same amount of that we're transferring back.
Right, the same amount of water under the same conditions, so same temperature and same pressure. So it will be the same amount of energy. And that's because of the law of conservation of energy. It's always true. Can't get around it.
Nope. Energy cannot be created or destroyed.
Yep, no matter how hard you try. But we can convert it from one form to another, and that's pretty handy. We use that all the time.
Sometimes it's fun.
All right, here's a question already. Look, how much heat? So we're on example 3 now. How much heat is released? Oh, this is going to be exothermic, right?
Exactly.
In kilojoules, if we have 2.5 moles of sodium hydroxide dissolved in water. So dissolving this base in water is going to release heat. Did you know that? Anytime you have to mix up a solution of sodium hydroxide, you might have to put it in an ice bath to keep it cool enough.
Really?
Yeah, it releases a lot of heat. And if you make too much heat, then you turn all your water into steam. So put it in an ice bath when you're dissolving this. All right, here's our conversion factor. Here's our heat of solution. So heat, kilojoules, is our target.
Okay.
And what should we start our T table with?
We should start it with the moles.
Yeah, let's start with moles. Delayed response, Nick. All right.
There's lag.
Yeah, now we didn't have grams here. You know, in class we always say, when in doubt,
Go to moles.
go to moles. But we already have moles, so
Go to
that
grams.
saves us steps. Don't go to grams. Our target is kilojoules. Here's our conversion factor. Let's just go straight to it. So mole goes on the bottom, that way we get it to cancel. And we'll put the number with kilojoules up top. That looks like a pretty big number. Remember the number for burning methane in a Bunsen burner was in the 800s?
Yeah, it looks pretty similar.
Yeah, this is only like half of that, but it's still, that's burning in a Bunsen burner. I'm going to let you do the math this time.
I got negative 1,112.775.
Oh, wait, 1,000, oh boy, I messed that up.
112.
Do over. Okay, negative 1,000, oh, now it's black. 112 and 7,
7, 5.
okay, 2 sevens?
Yes.
All right. Wow, I love the random pen change.
If you click on your marker, I think it'll change it back.
It will?
I believe.
Oh, nope, it's still black.
Then
Nick,
we failed.
It was wrong.
Once in a while, Nick
This is
did
the
something
first
wrong.
time of the day.
Okay, let's see. 1, 2, 3, 4 sig figs for moles. I'm not going to worry about these sig figs because that's a value that's been calculated by many, many scientists. This is our measured value. Yeah, so this is the one that's really determining our sig figs. So 1, 2, 3, 4.
Negative 112.8 kilojoules. Wait, no.
Nope, too many.
No, yeah. Negative 113.
Okay. 1,113 kilojoules is released when we dissolve that sodium hydroxide in water. That's a significant amount of energy, more than what is released by combusting that 1 mole of methane in a Bunsen burner.
Yeah.
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 Wow.
Yeah.
So be careful, when you're in the lab or even at home, if you're mixing things together and you're not sure what they are,
Don't.
yeah,
You
don't
should
do it.
do that first. Yeah.
Yeah, not a
Don't
good
even
idea.
do that.
Right. Don't go mixing chemicals if you don't know what's going to happen. Guess what? Our podcast is done, but that's not the only thing that's done. There's no more chemistry notes for this class ever. I know.
Okay.
What a great feeling. Woohoo. So that's it, guys. We're done with your last chemistry podcast. And the next thing we're going to do is review for the finals in class. You all have worked super hard this year, and I'm proud of you. Good job.
Do AP Chem.
Do AP Chem. Yep. Good advice, Nick.